If you recall, we've been doing stuff with partial derivatives this week, which is the same stuff that we did with non-partial derivatives, ordinary derivatives back in the day, way back in Calc 1, like a year ago from now. We find use derivatives, the first derivative to find linear approximations, and then yesterday we started using first and second derivatives to find and classify critical points. Things have changed because in the past, when I say solve f prime of x equals 0, it was just a one equation with one variable. We go through and solve it. I even made it easy yesterday by giving a polynomial. And I made it easy yesterday by giving a polynomial in two variables. The good news is we do the same thing. We take a derivative, the first derivative, set it equal and solve, set it equal to 0 and solve to find the critical points. The change is that we now have two derivatives and two variables. So we get a system of equations rather than just an equation. So this part, find critical points. When in the past we said solve the equation f prime equals 0, this has to evolve because I don't have an f prime anymore. I've got two first partial derivatives. This becomes solve the system gx equals 0 and gy equals 0. Because we have two derivatives for two variables. This just escalates. Once you make the leap to have dealing with two variables, if I give you a function of three variables, you do the same thing. At that point, it becomes easier. So if I give you a function of x, y, and z, you'll just solve a system of three equations. Oops, that's not three. That's three. Three equations in three variables. All right. So let's do that here. So we have g of x is 8y cubed plus 12x squared minus 24xy. Clearly, this problem is brought to you by the number 24. That's a Sesame Street thing. It shows you to be brought by the number and so on. Anyway. The partial of g with respect to x of xy. The 8y cubed is a constant term with respect to x, so we get 0. The derivative of 12x squared with respect to x is 24x to the first. And the derivative of negative 24xy with respect to x is going to be negative 24y. Y is a constant factor with respect to x, so 24x minus 24y. gy of xy. Taking the derivative with respect to y, 8y cubed, the derivative is 24y squared. The derivative of 12x squared with respect to y is 0 because that's a constant term with respect to y. And the derivative of negative 24xy with respect to y is negative 24x. In this case, the x is a constant factor. Here are our two first partial derivatives. We set these equal to 0, and this produces a system of equations. When you're dealing with a system of equations, your goal is to combine the two equations into one equation with one unknown. So that's the strategy. when you're solving linear systems, you had a very common set of strategies. So you could solve by graphing, you could solve by the elimination method or the addition method, or you could solve by the substitution method. And you went into great detail, or you can even use Cramer's rule. Everybody knows Cramer's rule, right? No one knows Cramer's rule. It involves determinants. That's why no one wants to know Cramer's rule, but it's fine. It's fine. So you spend all this time solving linear systems, and then we never spend any time in a specific section of a book solving nonlinear systems, because the instructions would just be like, I'll do something. Section 14.2, solving nonlinear systems. Do something. And you just have to do something that you know will work. In this case, we can eliminate the x. We can write, we can solve each of these in terms of x and set them equal to each other, or we could use that to eliminate the x. I don't know how you want to think about it. But the goal is to combine the two equations and two unknowns into one equation with one unknown. So our strategy, combine two equations with two unknowns into one equation with one unknown. I kept saying unknown, and then I wrote variable. Combine two equations with two variables into one equation with one variable. I saw you doing various things to make this happen. The first one is divide out the 24 all the way through. I like that. Use smaller numbers whenever you can, unless those bigger numbers are making something work for you. So in this case, we could take this one. If 24x minus 24y is equal to 0, we can either say x minus y equals 0, or we might interpret this as x equals y. In the second equation, we've got 24y squared minus 24x equals 0. We could drop out the 24, and we'll say 20. Immediately don't drop out the 24. Y squared minus x equals 0, or we could say x equals y squared. Now it's just a matter of perspective. You can see that the x, you could make the x's equal to each other. So someone might be thinking, make the x's equal. Or you might be thinking, plug the x equals y into the y squared minus x equals 0. I don't know what was going on in your head when you did this. Either one of these things is a valid strategy. The best one to do is whichever one occurs for you to do first. When you have this y squared is equal to y, or y squared minus x equals 0, this would look like y squared minus y is equal to 0. Factor out the y. And we get y is equal to 0 or y is equal to 1. Scroll. I guess I just gave away my read on the problem. The other version is the y equals y squared. Y equals y squared. The numbers that equal their own square are 0 and 1. So maybe you just look at this and say, I recognize this. 0 squared is 0. 1 squared is 1. These are only half the points. I've got 2 y coordinates. I need to find out what x coordinates they correspond to. So if y is 0 and y is 1, y is 0 and x equals y. So x equals 0 to go with that one. If y is 1 and x equals y, then x equals 1. So our critical points zero, 0, and 1, 1. Questions? How's everybody okay? Everybody's like, well, yeah, of course we're okay. This is how far we got. This is not what we came here for today. Stop doing recap. Show us the next episode. The second part, classify each critical point as a local maximum, a local minimum, or neither of those. We could use the second derivative, but there are 4 second derivatives. Before, in the one variable case, we just had to check the concavity of the function with the second derivative. Concave up, local minimum, concave down, local maximum. But there are 4 second partial derivatives. There are 4 second partial derivatives. Gxx, the derivative of gx with respect to x, the 24 is a constant factor, the derivative of x is 1. Minus 24y is constant with respect to x. So at least this gxx is a 24. We would read that as positive, so concave up. That makes sense. But that's only concave up in the x direction. What's going on in the y direction? If you look at g, y, that's the derivative of y with respect to y. We got the derivative of 24y squared is 48y. When y is 0, we get 0. That doesn't tell us stuff. When y is 1, we get a positive value. So at 1, 1 in the x direction, we got this concave up. At least we're hoping that interpretation still works. And in the y direction, we got this concave up. So what does that suggest about what's going on at 1, 1? It's concave up in the x direction and concave up in the y direction. What's happening at 1, 1? How would you classify that critical point? Seems like it might be a local minimum. That's very hand wavy of us, right? I mean, I was literally waving my hands about like with the concavity. Turns out we're right, so that's good. Oh, but this positive, negative, this concavity read doesn't work because it's flat in the y direction. And also, there are 2 other derivatives that I am conveniently ignoring right now. So our intuition. Looking just at these, xx and the yy. This is just us thinking about what's going on here. These 2 at 1, 1, positive in the x. So we're thinking concave up in the x direction, concave up at 1, 1 in the y direction. At 0, 0, we get concave up in the x direction, but flat in the y direction. Yeah, that's not helping. We get 0 in the y direction. Remember that the second derivative being 0 doesn't tell us what's going on. A second derivative is 0 for x cubed, which is a saddle point, and x to the fourth, which is a minimum. So no help there. Plus, there's two other derivatives. So let's write those down. What's the partial of g with respect to x, then with respect to y? Negative 24. And what's the partial derivative of g with respect to y and then with respect to x? Also negative 24. Notice that we got the same thing for the mixed second partial derivatives. I just pointed out that we got the same thing for the mixed second partial derivatives. So now you're starting to wonder if there's something about the equality of the mixed second partial derivatives. For well-behaved functions, those two will be the same. So here we say these are the mixed second partial derivatives. Mixed second partial derivatives will be equal. But this raises the question, how do we use these in our analysis? How are they going to show up in our analysis? How do we combine all four of these? So what we're going to do is we're going to look at this. This is and we're going to make a matrix out of these four second partial derivatives. We're going to make a 2x2 matrix called the Hessian matrix. That's irrelevant. We're going to find the determinant of this Hessian matrix. And that is going to give us a function that will help us classify critical points. Oops. I'm going to drop the XY. It's just too much. No, it's not. Here's why I had to point out that they were going to be the same. So we're gonna do gxx times gyy minus gxy squared. Gxy squared is just gxy times gyx. They're the same, so we're just gonna square the first one. This is what we're gonna run our critical points through. This is one function made up of the four, really four second partial derivatives. Very cardinal. I'm sure there are only 3 second partial derivatives. There are 4 second partial derivatives. Has everybody seen Star Trek: The Next Generation? Just me? It's okay. That show is older than like everybody in the room except me, so I would not be.
Does that make you feel old?
No, the fact that some random joint hurts whenever I wake up, that's what makes me feel old.
The freestyle on working legs.
Yeah.
That's expired.
Yeah, the free trial on painless walking that has expired. Also, the free trial on clear vision that I'm looking forward to clip to re-up on that one, but obviously I can't see it because I don't have the vision anymore. I used to have vision that worked reasonably well up close and far away with one set of lenses, but now my eyes are like, oh, nah, fuck that. We need something fancy now.
Don't worry, I understand my freestyle expired too.
Yeah. All right. All right. Eyes are such an amazing piece of technology and so poorly designed. I mean, it's just kind of ridiculous. It's like you have a camera and then it's like, oh yeah, the mount for the camera, the thing that's holding the camera up is like right in the middle of the camera. So we have to use software to fill in what's going on in that space that you're not actually seeing anything. Do you know what I mean? It's terrible design. Anyway, that's all beside the point. That was just to give you time to copy this down because it's very fiddly in its details. And I, for some reason, chose to call this function G, so it would look like all the Y's all over the place instead of F, making it distinctive, but there we are. So here's how we use this second derivative test. If at each of these points, if D is positive, and if fxx is, no, it doesn't matter, it does. If D is positive and gxx is positive, then local minimum. This fits with our intuition from before. We're thinking of this as being concave up in both directions. Concave up in both directions. Case 2, if D is positive and gxx is negative, then we have a local maximum. This is the same intuition that we had before. Concave down, because gxx is negative. concave down. We're thinking concave down in both directions, telling us local maximum. So our intuition is the same, just the other direction. There are two things that happen if this this determinant function is positive. If this determinant function, if this D function is negative, then we can conclude it's a saddle point. That's neither a local maximum nor a local minimum. We get a saddle point. Our intuition in this case is that we're concave up in one direction, concave down in the other direction. So we're standing at this point where things are flat. If we change in one direction, we'll be going up, so minimum. But if we go in perpendicular to that, we'll be headed down, local maximum. That's why we call it a saddle point, because the saddle point has like the part that you sit on, and then the part that goes up and behind, in front of you and behind you. So our intuition here is that it's concave up in one direction, concave down in the other direction. So our intuition here is that we're concave up in one direction, concave down in the other direction. Notice that when D is positive, we're just looking at GXX. When D is positive, we're just looking at GXX. What about GYY? How can I say we're concave up or concave down in both directions just by looking at one of them? So when this D function is positive, look at how it's constructed. I'm multiplying GXX by GYY, and then I'm subtracting the square of GXY. I'm taking GXX times GYY, I'm multiplying those two things together, and then I'm subtracting something that I know is going to be positive. If I end up with a positive number after doing all that, it tells us that GXX and GYY must have the same sign. That's why I only have to look at one. If D is positive and GXX is positive, GYY has to be positive as well. Otherwise, we messed up. Or complex numbers have snuck into our problem, and we need to get them out of here. So get out of here, complex numbers. This is real analysis. I mean, calculus. So when D is positive, that's telling us that GXX and GYY must have the same sign. That's why we only have to look at one. We just look at what GXX is doing, because GYY will be doing the same thing. If D is negative, that's pretty strong evidence that GXX and GYY have opposite signs. Or there's something very powerful going on in this term. Let's forget that I said that. And just say if D is negative, GXX and GYY probably have different signs. So that covers everything that could happen, right? That covers all of our cases, right? You can clearly tell that the answer is no. What have I left out? If D is equal to 0, then we get nothing. Good day, sir. If D is equal to 0, then this test doesn't work. It doesn't mean you say, oh, I don't know. It means you have to do something else. This test isn't going to tell you. So if D is equal to 0, then this test provides no conclusion. This doesn't mean that you just write no conclusion. This goes back to like your sequences series, power series. Like, does this series converge? And then the ratio, in the ratio test, if the limit from the ratio test is equal to 1, then the ratio test provides no conclusion. You don't get to say no conclusion. The series either converges or it diverges. You have to figure out which one it is. You just can't use the ratio test to do it. You still have to figure out what's going on. You just have to do something else. If you're wondering what else to do, the easiest thing to do would just be look around. What's going on near that point? If I move off that point a little bit.
It's the mid.
Well, we just have to make sure that we're moving off the point close enough. That nothing weird happens. Any questions? How's everybody okay? There's a lot of things that could be going on at this point that'll cause it to be a saddle point. It could be, like I said, concave down in one way, concave up in the other way. There's a lot of weird things that could go on. It could be like an x cubed in one direction and then a different x cubed in another direction, kind of like a more of a chair point than a saddle point, because you can slide off the front of it. It might be a parabola one way and a cubic in the other direction. It might just be like a couple of x to the fourths where it's just going to zero out everything for a while. So a lot of things that could happen to throw that D equals 0. It doesn't mean we're off the hook for classifying the critical point. It just means we have to do something else. The easiest thing to do is throw numbers at it. When in doubt, get more data. Any questions? Comments? Snide remarks? How's everybody? Everybody looks so sad. Did I ruin the game by telling you how it was? I know all of you are like, oh, determine the Hessian matrix. It's exactly what I was thinking. And then he ruined it by just telling everybody. Then the person sitting there said, well, we were all thinking the same thing, so it's all right. It's all right. Questions? Yeah. Yeah, so you've got this critical point. You want to know what's going on around because the second derivative isn't saying nothing, right? It's like the mobster on The Simpsons. I ain't saying nothing. So just like from that point, see what happens if you change x a little bit up and down. Do we go up on both directions? And then what happens if we change go in the y direction in both directions? look at some points around that point to see if we're always going up. And then it would be not conclusive, but it would be safe to conclude that there's something like a minimum or a max going on at that point. Or if you see going up in some directions, down in other directions, it's gonna be a salad. Just look around. When in doubt, look around. Is that okay? So in this case, for our example, our d of xy function will be 24 times 48y minus a negative 24 squared. We can see that this is going to be positive at 1, 1 and negative at 0, 0. I don't know what 24 squared is. So this determinant is how we put together the 4 second partial derivatives into one function that we can drop our critical points in. Any questions? All right, so we're gonna practice this tomorrow. Tomorrow is all about vectors, so set your Wayback Machine to vectors. Stuff from chapter 3, also whatever stuff from chapter 12 that was about linear functions, equations of planes, know about normal vectors and all that jazz. That's it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing.